That should be us with audio now, hopefully. If you can hear me loud and clear, it would be great to just get a message in the group, in the chat, and then we can make sure we're all up and running. We've got some people with us already, I see. That's great. Like I say, you never know what's going to happen here. So, if you are ready to start, we'll get going. The whole purpose of this stream was I made a promise a while ago now that if we made 3,000 subscribers, we would run the whole welding inspection training program that we have free online. The idea here is we really want to break the need to pay for knowledge, right? There's always going to be the need to pay for qualification because that's how the world goes round. But for you to be doing whatever certification you want to do, whether that be C-SWIP, AWS, CWB, ASNT, SNTTC1A, whatever, knowledge should be free for all. And YouTube gives us a really good way of being able to do that. So we make absolutely zero money from this. I think we're currently making like $15 a month off views, but we do it because we want to push this knowledge. So your interaction, the likes on the videos, the watching of the videos, sharing, building the community, we've since hitting 3,000, we've actually grown quite quickly within the last couple of weeks. We've added another couple of hundred subscribers. So that's all we ask. Just keep the conversation going around the channel and keep asking questions, and we'll keep trying to answer them. Helping me today, we should have Rob in the chat somewhere, if he's managed to sort his computer out. That Rob works with me. He owns his own company called All Arcs Limited, who runs the qualification side of what Carbon Arc do, which keeps us separate from our consultancy and our qualification. And Rob has agreed to join today just to help to make sure that there's somebody else in the chat making sure any questions are being answered or questions are getting raised back to me. So please ask as many questions as you want. Today, we're going to do welding processes. There is a lot to cover with welding processes. Just to go back to a question we had in the chat before there, was what do I think about the level of or the quantity of information that's needed, I guess is the shortened version of this for the qualifications. I think the qualifications ask too much in some areas and not enough in others. So one of the big things is C-SWIP, for example, one of the biggest ones, we use that as the example most of the time, asks a lot of questions around MMA. MMA is still a really important welding process. It's something that we need to make the world go round. It's versatile, it's portable, it's relatively inexpensive for the process, but a higher skill level and stuff. So some certification schemes ask a lot of questions around that because it's easy to ask a lot of questions, is my view. When we do MMA in a little bit, you're going to see a huge amount of variation in multi-choice questions, for example, because you can ask about the electrical characteristics or the million different types of electrodes, how you control the electrodes, damage, inspection, lots of defects, so naturally they get gravitated to a lot in an exam selection. But does it mean we need a lot of it? Probably not. I wish we tackled more quality control type questions, NCR working, communicating our findings with our clients. I wish we had a way in those big qualification schemes to check your ability as an inspector to communicate what you found. And so yeah, it's I could get lost in that question for a while, but we have to kind of teach you to what the schemes require. If you look at something like ISO 9712 for NDT, that has quite a detailed philosophy for the content, given the percentage of time you need to be teaching on different subjects. So that kind of pushes you to go one sort of direction when you're dealing with those ISO type backed qualifications, right? But hey, without further ado, I'm just making sure we still got everything online. Please give me a shout if nothing is kind of doing what it should be doing. And we will go from there. I am working on a new setup for streaming. So hopefully we can kind of start to do some different things like that. I should have changed the screen. For those who this is your first time joining our content, quick introduction about me and why I do what I do. So I started my welding apprenticeship all the way back in 2003. I served an advanced modern apprenticeship in the UK, which was a 4-year apprenticeship. There's actually above my head here is I got Apprentice of the Year. So there it is, back in 2006, 2007 is there. I primarily did my apprenticeship as a TIG welder, and I worked for a company which gave me quite a lot of scope to do a lot of different stuff. So I did everything from aerospace to Formula 1 wind tunnels, ship exhaust systems for destroyers and stuff like that. So it was a really cool apprenticeship. We did that. I joined TWI back in 2008 as a lecturer teaching. Initially I was meant to be teaching NDT, and I did that for about 3 months, and then was moved over to the C-SWIP Welding Inspector course, which I did for a while. So we did for a few years in all over the world. It was great. It was when the TWI still had a really small weld inspection team, so we kind of just went everywhere and taught Europe, India, you name it, and did that. And then in 2010 I left the training side of TWI and joined ARCS, which is the welding engineering team at Cambridge. I was based in Middlesbrough and became a welding engineer and kind of did all that. In 2013 I left there and took over as lead welding engineer and technical authority for Technique FMC, running welding and NDT for subsea engineering. So this was a subsea umbilicals. This is primarily duplex, a little bit of 316 stainless steel, but mainly super duplex. And I ran the teams in UK, Angola and Houston, welding engineering, all the way from project tender to project delivery and aftermarket stuff. So that was cool. And then we started Carbon Arc in 2020 with the goal to kind of improve the way people get training. We love training. I love sitting in front of you guys, engaging with you during the courses and helping you guys get to wherever you want to get to, whether that be just individual in a direct company role, or to move out and hopefully start your own inspection companies one day. That would be great. So that's me in kind of a nutshell. Right now Carbon Arc do everything from training to MOD consultancy work. We work on weapon systems and all sorts of things. It's a really exciting time, to be honest, and hopefully we'll share that with you guys. And the more we learn from all these different work scopes that we do as welding engineers on the consultancy side, we bring into the training and share with you as much as we can. Okay, so that's very quickly that's us. I've got buttons here so I can turn around. If you ever have any questions, please just communicate with us. YouTube channel's brilliant because you've got the questions under the videos. just ask them, and we will do our best to get to them. It is difficult. We're kind of balancing it with a lot of other work, but we will try to answer them. Okay, so let's just a couple of questions. Make sure we catch up. Okay, so everyone has audio. That's great. Do you think just 2 days of training are enough after study? So I'm going to guess you're questioning the C-SWIP route, because you can do online study and then go and do your practical training, and away you go. It should be, even if you did your 1 week full training, you would only get about 2 days practical. So they're just kind of rebalancing the way it's delivered. Do all your theory at home, and then come back, do your practical training with the samples, and then go. Like with anything, it depends who you get teaching you, who's doing your practical. It can be good and it can be bad. Try to get as much practical knowledge before you go to that training as you can, and that's going to give you the best chance of passing. But it is possible to do. Okay, it's we've got that. Okay, so first place is to start, and today we're going to do welding processes. We're going to do all the processes, so that'll be your MMA, TIG, MIG-MAG, flux core, so on. Okay, the main core things of knowledge you need. This would normally be kind of like the first day of our training if you came to Carbon Arc to do it, and we would be doing this in the workshop with the welding processes. We're kind of limited to that, so what we've actually done is we've taken VR, AR images through our Seabury system, our Soldermatic, which is an awesome AR welding training system, which allows us to really talk about welding processes, especially online. So we've got some videos which we'll walk through, and we'll do that. Okay, but the first place really is to start with the history of welding, so we get an idea of where we are, because a lot of the history gives you a good grounding of why we have what we have, and why we have those sort of, I want to say, like 5 main arc welding processes, and how we got there. Okay, so right, so we always start with a thing, say welding started a long time ago. Depends what your definition of welding is going to be. If that's going to be forging, so heating material up and driving it together. Okay, so blacksmiths have been doing that a very, very long time. We've got evidence along with some really, I'm sad, really cool items. Like in India, there's the iron pillar, which is thousands of years old, which looks like to have been forge welded and is still standing. The chemical composition of that steel makes it fairly weather resistant, so it stands and feels quite good. But in essence, what we're doing is we're heating the material till it's red hot and then driving it together. Works really well on soft materials, gold, bronze, brass, stuff like that we had early on. The stuff that was fairly easy to make. Okay, and it's still going today. It still sits a very good purpose, and we use it a lot. Then going through into the Middle Ages, okay, you're getting the need for refined technologies, and technologies which don't only do a practical output, but meet an aesthetic need as well. So, armor, very expensive, only for the elite. They don't just want it to protect them, they want it to make it look good as well, look empowering and imposing on the battlefield. So these things had the flair put to them as well, so you get all your metalworking development and stuff coming through the Middle Ages. And then when we get to the 19th century, hundreds, we hit quite a rapid investigation and findings and development of what we see as arc welding today. Okay, so once we started playing with electricity, some clever people, the Victorians, had a lot of time to do a lot of different things. It was basically just play, see what happens. Now, there's a guy called Edmund Davy, so he discovers acetylene, which kind of pushes gas welding. But actually, just before that, you had Humphrey Davy, who discovered that he could produce an arc between two carbon electrodes. Now, once you start to think, well, I can produce an arc and it gets hot, we can then start to play with the ideas and the applications of where that happens. So that moved to what you see on the top. So here's Humphrey Davy, a picture of him here. And above him, you've got that carbon electrode apparatus. So we've got like a nodding donkey type toy fixture with a carbon electrode which could have electricity pass through it, and then the tip of the electrode we could produce an arc. And you also use that for an arc light as well as the initial, the bright arc. We know how bright a welding arc is to use as a light, but use the heat to drive melting, you can start to get welding. Okay, and that's 1881. That's where you start to get that with Augustin de Martinez, who uses his carbon rod to melt lead plate and start to make batteries with that. And then you get the big change in 1885 into the 1890s with Benedos, and I can't say these names, I'm sure it's terrible, but Polish and Russian inventors who really show that you can start to use electrodes like we have today in MMA to drive welding. And really from 1885 onwards, that's MMA, right? So it's our first main welding process which really drives the industry forward. But right now we don't really have an industrial need for it. Okay, most things are made from steel or riveted. Shipbuilding in the main is the big thing here, pressure vessels. So we need to kind of find a reason to be welding next. But the technology is in its infancy, and it's starting to be proved and work through what we're doing. Okay, so of course you need a war. Most things kick off when we have a war. So we went through the First World War into the Second World War. We saw a massive push for the need for welding in especially World War II. So we have things like the Liberty ships, which we talk a lot of about, because these were the big drivers to move from a riveted system in shipbuilding to an all welded system, mainly for the speed of manufacture and how fast we could produce container ships, merchant vessel, cargo ships to move from America to Europe. In the war as well, we then start to see the need for things like sorry, is the music a bit loud? I can't hear the music on my side. I can drop it right down. Hopefully that's better. Tell us if that's better. We've got the need to join aluminium or lighter materials for fight, which then drives the invention of tungsten inert gas called heliarc at one point, as we play through it. We then drive submerged arc for bigger, heavier applications and really pushing all that development. And it is, the war, we don't need to state how bad that is, right? It is very bad, but for the technology of what we have today, it was instrumental to driving it forward. And of course, that's what will always happen. You can have a good idea for a technology, but you need something that drives a whole sort of community forward to hit that. Okay, and of course then you have to pull through all of that thing, which is the really exciting stuff today. I was at a talk a couple of weeks ago at a company called Nesset in the Northeast, who put on an ARC event, which is I was lucky enough happy enough to be invited to talk about the future of training. There was a robot company there called Bobot, who are working on the simplification of programming to allow robots to be much easier to program and drive. But at the same time, we've got to remember that robots will not replace a person for a long time. You know, we need welders. We need people who can look at a application and an output and make a decision based on a holistic thing. So everything that's together, which is still not really tangible on a digitization side, but digitization methods to help us make better, more informed, more accurate decisions is where we're going to be moving to, and we need to move to, you know. And it's going to make things more sustainable, safer, better, more accurate. Yeah, so that's where we're going next with that. Okay, so that's our very quick potted history of welding. 1800s really where we're starting. Development of MMA first, and really MMA hasn't changed since then, but all the other welding processes we have are still fairly new, really. World War II, 1930s, 1940s, most development around shielding gases and the understanding of stuff, 1960s, 70s, 80s. And we're still learning. We've still got advanced processes now kicking in, like electron beam and friction stir and all of that stuff that needs to kind of move forward next. And we'll all find its very positive niche on how it applies. Okay, so that's our welding. So our next bit is going to be, you know, what is required to produce a weld. These are our input controls and things that as inspectors we're going to have to keep an eye on to make sure that the input gets the right output. You know, bad in, bad out. Okay, so we've got to make sure this is what's controlled. Okay, so in the main, we can characterize our inputs into welding into 3 groups. Okay, so we need heat. We need to protect the molten weld pool from the atmosphere. And then we need to somehow balance our mechanical properties and make sure we can maintain things like strength, ductility, toughness. Okay, in the main. So heat. So on average, steel melts. And I use this on an average when I'm teaching these courses. We've got to kind of put a number in the sand somewhere. So I go with steel melts at about 1400 degrees. Okay. It changes depending on your alloy, but let's just give it a number, right? So we need to get our steel above 1400 degrees to make it molten to then drive a weld, to manufacture a weld. In order to do that, we use our electrical arc, using what Humphrey Davies kind of found with his arc light, and then was moved on to the from the copper contact to the lead and all that. We produce an electrical arc which has an average temperature of about 6,000 degrees. So that's about the surface of the temperature of the surface of the sun. So really, really hot, but well above 1400 degrees. So why is that needed? Okay, and we need a 6,000 degree pin sort of point temperature, because as that heat is moving into the workpiece is pulling the heat out and dissipating it across a big area, so the heat's being shared. We lose some of the heat into the atmosphere, you know, some of the energy changes to sound and light and all that type of thing. So we need a high pinpoint energy to get the material in the weld pool to the correct temperature for us to be able to deal with it. Okay, so we need to produce that. In the main, we use an electrical arc to produce that, but we can use other things like gases, so acetylene, propane, all different efficiencies. Not as good as an electrical arc, but you don't need power source. You can just have a gas bottle and away you go. We could use electrons. Again, it's a power source, but it's not an electrical arc for electron beam or laser welding, all that type of thing. But it's all to do with getting some type of heat to the part. Okay. We then need protection from the atmosphere. So the atmosphere, the general air, if we look at it and break it down, it's made up of a lot of different constituents. Right? So can anybody tell me what the biggest makeup of air is? And we'll make sure everybody's still hearing us and everything's okay as we go. Okay, what's the biggest element in air? Hopefully someone gives us an answer. I'm just staring into the dark. Yeah. Maybe. Should we go for it? It's always never know on my side because of the delay how long I wait. Okay. The biggest, yeah. So we've got hydrogen. So we've gone with hydrogen. Biggest one. Well, the biggest one. Thanks for at least somebody put a guess in, right? The biggest one there is nitrogen, 78%. Then we've got oxygen at 20%. So by far, the biggest makeup of the air is nitrogen and oxygen. We've got a little bit of argon is under 1%, and everything under that, you can see how many decimal points we start getting really, really quickly after that. Right? Now, one of the problems we have is molten metal, especially steel, is affected by these elements. And in the main, some of the things we really don't want getting to a molten material is nitrogen and oxygen. They are going to cause different types of issues. So oxygen is going to cause a hell of a lot of oxidization. So this is porosity, contamination, coking in the case of something like stainless steel or something like that. Nitrogen can form nitrogen embrittlement. So we kind of want to get rid of them in the main for a standard steel. But in some cases, we actually want to add a little bit of it. If we look at stainless steel, shielding gases have a small amount of oxygen in it. Super duplexes, shielding gases have either like a back purge is 199% nitrogen. If we have a shielding gas, it's 2.5% nitrogen with an argon mix. So we might want to put small amounts back in, but in the main, we want to get rid of them. Okay, and then control what we put back into the system. So we want to surround our molten, which we're applying the heat to at 6,000 degrees, with a gas isn't going to react. And as the mainstay, that tends to be argon. Argon is relatively easy to get. We can pull it out of the air, just under 1%. We can pressurize air down and pull off argon and generate it like that. It's relatively heavy, so it'll form at the bottom of a weld and build up, so we can produce a nice sink of argon sort of shielding gas in there, and then we can go from there. Some other gases we might use, something like helium. Helium's very light, So we have to use it at much higher flow rates, and it's very expensive to get. You can't just pull it out the air. We have to capture it in certain outlets in the world, and so it's much more expensive. But in the main, we're going to go with argon is our shielding gas. We might mix it with argon CO2, argon helium, all that type of thing. But argon's our mainstay. Okay, stopping the contamination of the other elements which will affect the molten material at 6,000 degrees. Then we've got to look at our mechanical properties. Okay, so what are we going to need that weld to do? Mainly, we think about strength. So what is the yield strength of the material? How much strain is it going to be holding in its application? If it's a bridge or a building or a pressure vessel or something like that, we can calculate that. We can use our equations to work out hoop stress or whatever sort of we're working at, tensile stress, and decide the thickness of the material and therefore the strength it needs to have. We can then play with that in the weld by the filler material we use, so the welding consumable. Our welding consumables are multi-range. You can go to most suppliers and say, I want to weld an S355 J2 steel, and they will give you a selection of welding consumables for whichever welding process you're using, which will have the right amount of alloying content in them to be able to maintain that strength in normal operating activities. We're going to talk about this in a session later on, where we talk about metallurgy, because as weld inspectors we kind of need to understand why we're controlling these things. So we'll introduce the likes of the effect of carbon, manganese, nickel, chrome, how all that kind of goes together. You are asked that, especially at sort of level 2, sort of C-SWIP 3.1, CWI, all that type of thing, CWB. Kind of want you to understand the basics of these types of things, so we'll look at that later. But in the main, for us as inspectors, what we're going to do is say, well, we're working to a welding procedure. That's going to tell me my amps, my volts, my travel speed, and therefore my heat input. So that's how we control our heat. The WPS is going to tell us the shielding gases we need to use and we need to check against. Great, a nice easy one. And then it's also going to tell us the welding consumables we're going to use. But on top of welding consumables, we'll also have heat input control, post-weld heat treatment, different things we can do to improve mechanical properties, and then we go from that. But in the main, we need to test for these. So again, in a future session, we will also work on mechanical testing and which mechanical tests show us that we're maintaining these properties in the way we need to do it. So this is bend testing, tensile, sharp V-notch, hardness, CTODs, all that type of thing. Okay. Different standards have different requirements. In the main, they're generally the same intended output, but we use different measurements, whether it be imperial or metric, different locations we might be looking at, but the same output overall. So we've been talking about sort of heat input and the amount of heat we need to put into things. So we need to start looking at the electrical characteristics of a welding arc. Now, in order to produce an arc, we need a couple of different things, okay? Now, we need to initially start with a power source, which we're going to start pushing electricity through, okay? This can be a fairly, I haven't got the right word for it, what do I mean? It can be a concept which is difficult to imagine. So the way we try to talk about electrical circuits in the main is thinking like with a pipe full of water. So what we're going to have is we're going to have a pipe of water, at one end is going to be a pump, and our water is our electricity. So in order to get the electricity to move, we need to have a pump working. Now here, our pump, the power of our pump is our voltage. Okay, so this is our force pushing our electricity through our pipe. Okay, now in open circuit voltage, so this is where we have MMA MMA process. We drive a fairly high open circuit voltage first at around 80 to 90 volts, right? So there's no welding, but the electricity is trying to be pushed through. When we bring the welding electrode fairly close to our workpiece, there's now an arc gap that the electricity can jump at 80 volts, and then the electricity starts to flow. Once it's flowing, the pump doesn't need to work as hard because it's already flowing and there's a connection and it's working, so the voltage drops down. Okay, so we'll go from like 80 volts down to 20, 30 volts, something like that, right? So this video here is trying to show voltage in that effect. So here's my welder. We were busy working on some S690 procedures at the time, and I thought I'd get a video of this quite quickly. And that was so you can see that the start is 68 volts, and when we arc up, it's going to arc and drop right down to the working voltage of the piece. So there's the voltage. So there it's fallen down to about 22, 24 volts and bouncing around. Okay. The reason it bounces around is because voltage is dependent on the arc gap, and as the electrode melts back, the arc gap gets bigger, which means the voltage goes up, and then when the welder corrects by pushing the electrode closer to the job, the arc gap comes down, so the voltage goes down, but then melts back again. And the welder here is maintaining a gap, but it's not consistent, so it bounces as we go along, and we try to drive that. So that's our voltage. Our voltage is our pushing power of the electricity through our system. So there you go. I love this picture. So we've got a man of voltage pushing our amperage through the system, but as the amperage is pushed, we have resistance, which is measured in ohms, trying to restrict that flow, right? The longer the pipe, longer the wire, the more resistance there'll be because there's more to stop that amperage flowing, okay? So the longer the wire, the more push you need, so the higher the voltage. Now, what we see in welding is the further away from the workpiece we are, from the power source. So we've got our welding set. Let's say we have a meter away. The cable's a meter. If I measure at the power source and at the workpiece, I'll get one measurement. If I then increase the electrode wire, so the torch cable, to 2 meters, I'll then get a reduction. And if I increase it more, I'll get a further reduction. So what we end up having is a difference in the measurements between the workpiece and the welding set, which we have to keep an eye on. And this is called voltage drop, which means that for certain testing positions, so when we're testing voltage, we need to be doing this as near to the workpiece as possible. Okay, because the further away we are, the less voltage we will actually have at the workpiece. So to get 20 volts at the workpiece, we might need to have 30 volts at the power source, say. Okay. All right. I'm just getting a message here that the chat has dropped out. So if you're asking me any questions in the chat, I'm sorry, at the minute I can't see. So I'm just going to see if this test comes up. Can anybody tell me if that is still working or not? As I just kind of make sure we are where we are. It doesn't seem, I've just put a test in, it doesn't seem to be coming up for some reason. Hey, YouTube is brilliant. Yeah. Okay, let's just see if that pops up because of the delay. I don't want to miss anybody's questions as we go through this. Let's see if that comes up in a second. Right, so that's our current. So our current is what we're pushing through with our voltage, which has been restricted by our resistance. The further away we are from the power source, we get a voltage drop. Yeah, right. What we can then use to kind of how we the polarity is the direction of the flow of that amperage. So we can either use DC electrode positive, DC electrode negative, or AC. Now, if you're struggling to remember which one's which, in general, we kind of fall into three groups. Okay, so if it's MIG-MAG, flux core, MMA, sub-arc, generally it's DC positive. TIG is DC negative. Aluminium welding with TIG is AC. If you can kind of remember those three, it's going to give you a rough idea on where things are and how kind of that falls out. Okay. Right, so hopefully, I'm sorry, I'm just looking there, I've still got no chat, which is a bit of a pain. There's no real way for me to refresh it, is there? No. Okay. Right, hopefully we're still on and we're still working. Am I getting some messages come through here? Okay, I'm getting some sort of coming through. Right, there we go. So remember those three. DC positive is for your heavier processes, MIG-MAG, flux core, sub-arc. TIG DC negative, TIG on aluminium, AC, and that should get you a good position to start from until you can just get them into your head. When in doubt, we work. Okay, right. So polarity here, that change in polarity between DC negative, DC positive, and AC. What it's doing is it's balancing the where the heat is in the arc, really. Okay, so with DC negative, what we're saying is most of the heat is in the workpiece, about 2/3, okay, of the heat is in the workpiece. With DC positive, we swap and spin that round, and most of the heat is in the electrode. And then AC, it's about a 50-50 balance. Now what this is going to do, as you can see on the drones here, is by changing the balance of polarity, we can either get the material melting more or the electrode melting more. And what that does is it either makes one more penetrating than the other, and we sort of play around with it. Okay, don't get lost too much in this, right? Kind of just go with the processes I've said and what the polarities are. When in doubt, it'll be on your WPS and we can run with it because they're just the standard ideas. But as welding engineers, we often play with polarity to do lots of different things. Okay, but the big thing here is the magnetism that we produce in the system. Okay, magnetism can be a bad thing for our welding arc, and it can drive to what we call arc blow, right? So this is where, as we are moving the electrode round, because it has its own magnetism, any magnetism in the system, so in the part, can actually start to make that arc deflect. The direction that the arc deflects will be dependent on its polarity. Okay, and you might be able to switch its polarity and get rid of the arc blow, or it might just make it worse. Right, and then we have travel speed. So last big thing controlling the heat input and the amount of heat we have in any of the welding processes. In the main, we see this is controlled by the welder. Okay, if it's a automated set, something like robotic welding, it's a robot. But let's just keep it with, we're involving people at the minute to keep it easy. Controlled by the welder, and it's the movement we go from A to B, right? We often measure it as a run-out length as the term we use, even though run-out length is mainly an MMA statement, but it's how long it takes us to get from A to B, right? So if I've got a stringer bead, you can, in a weave, you can see if I go on a stringer bead from A to B and I measure for a minute, I'll get a distance. But once I start to weave and I go up and down and walk the cup and make it all look pretty and everything welders want to do, what happens is that weave will shorten the distance we've traveled from A. We're traveling left and right as well, right? So for the same amount of time, we travel a shorter amount of distance. Now that distance being reduced increases the heat input. Now heat input is one of the biggest things we have to control during welding, and we have control over during the application of the process. If we allow heat input to go through the roof, we tend to see reductions in toughness. If we travel too fast, we see a reduction in heat input and we see a higher hardness value. And either one can be a bad thing. But this concept drives a lot of the questions we see in weld inspection. Okay? Everything to do with, if you increase amperage, what will happen? Well, an increase in amperage will make your heat input go up. And we're going to talk about heat input calculations and that later. But up in the amperage, higher heat input, low toughness. Reduce your speed. More heat in a smaller area is a higher heat input, reduction in toughness. Okay, toughness means that it's going to absorb less energy at low temperatures, so it's more likely to break when we reduce the temperature beneath -0 degrees. If we increase the travel speed or reduce the heat input, the hardness value goes up, which makes it more brittle. So both are bad, and we don't want to do that, which means that as inspectors, we want to be looking at the weave width that the welders are producing. This is normally in the welding procedures, where we will see a maximum weave width of 2.5 times the electrode diameter, or no weld is to be more than 12 millimeters wide. There's lots of ways we can do it, but this is why we have to do it, because we're not going to be maintaining mechanical properties in the correct way. But a lot of welders like to weave their cup because it looks pretty, but it can have detrimental effects to the mechanical properties of the weld if that wasn't originally qualified and accounted for. So there you go. Right. So that's how we deal with a welding arc, and everything we've covered there is generic across all of our welding procedures. So we have a heat source, we have to protect it from the atmosphere, and we need to maintain the mechanical properties. Mechanical properties controlled by the consumable we're using and the heat input we apply. We protect from the atmosphere by using a shielding gas, and we produced a molten pool by our arc, our electrical arc, or blue light, which is burning at like 6,000 degrees and melting the material underneath it. So those three things are our welding. How we produce that is what is different between each of the welding processes as we go. Okay, so I can see we still don't have a chat, and I've got no way of making it work on my side by the looks of it, which is a pain. I got a message here at 9:11. If anyone can try and drop one in and just say this is my test or something like that, then we'll see where we are. Okay, we will make sure that we kind of capture all questions after the stream, if I get them back up or not. And if your question hasn't appeared when the stream is uploaded fully after this, please just re-ask your question in the comments, and I'll make sure we capture them. Okay, right. So we've done our three things that all welding processes need. Now we need to look at our different welding processes and how they fall out with each other, right? So what we do here is we put welding processes into groups, okay? Now, so we have got welding across the top, and what we've already kind of covered by looking at the history of welding is that we can have different types. Now, to make things a little bit easier for us, what we're going to do is we're going to split them into two. So we're going to have fusion welding, which is molten processes, and then we're going to have solid state welding, which tends to be friction stir, where melting does not occur. Okay? And that's where we kind of fall out. So under fusion welding, you're going to have your gas, resistance, arc welding, something we call newer welding, which is the electron beam laser, and thermite welding, which is weld which is used on train tracks. Okay, so a powder with a block of steel in, once you light it, it doesn't stop. Okay, but everything under fusion are all molten materials. Solid state, so on our friction, we've got ultrasonic, forge, and cold friction processes. So this is your friction stir. What happens with this process is the material is heated to its plastic state, so it's never molten, and then we mix it together. Okay, but for us, in our generic welding inspection frame and qualifications, we're only really looking at arc welding. It's good to kind of have an appreciation that there are other welding processes in play, but it's not a big push. Oh, thanks, Brody. Brody's just dropped a test in there, and I can see that. So at least that's there. Okay. Right. So under arc welding, we have manual metal arc (MMA), tungsten inert gas (TIG), metal inert and metal active gas, flux core, and just off the screen for some reason, can I open the screen up a little bit more? There you go. We have submerged arc welding. Okay. The terms we're using here are British or European standard terms, but of course each of these welding processes also has an American designation as well. Okay, so MMA, manual metal arc, in America is shielded metal arc welding, SMAW. TIG, tungsten inert gas, is gas tungsten arc welding, or GTAW. MIG-MAG is kind of pulled into one grouping, and it's GMAW, gas metal arc welding. You got your flux core and then your sub arc as well, all the same. Okay, it's good to know the difference, because if you're using an ASME standard or an AWS, they will refer to the same processes with their different names. Okay. Now, underneath that arc welding, what we can do is we can split them processes into two further groups, okay? And this puts them into either manual or constant current processes, or semi-automatic, which are constant, that's spelt wrong, constant voltage, okay? So we've got constant current and constant voltage, right? Constant current is manual metal arc, tungsten inert gas. Constant voltage is metal inert gas, metal active gas, and flux core, right, is our main. Now, sub-arc can sit between the two, right? Depends on the amperage level it's working on. If it's below 1,000 amps, it'll be constant voltage. Above 1,000 amps, it becomes constant current. So it kind of moves around depending on where we are. Okay. Now, what does this mean? Why do we have constant current and constant voltage? Okay. Well, it's going to be how these welding processes drive how the arc works, which we're going to cover when we do the next point. Okay. So we group our materials, group our welding processes. We can go further into grouping processes as well. In European standards, we can number our processes as well. So MMA is 111, TIG is 141, MIG 131, MAG 135, flux core 136. It kind of can be infinite in the way we describe welding processes. If you're doing your C-SWIP, it's good to at least know the main sort of 5 arc welding processes and their numbers. Do drawing symbols, that's where that number is used a lot. In welding procedures and welder qualifications, the numbers are used within the designation of an EN 9606 qualification number. So it's good to know them and to be able to identify them. Okay. Next, we're going to do our manual metal arc. So, like I said at the beginning of this stream, one of the things here is that I do believe that the qualifications over-egg the reliance on some of these processes, but at the same time, with something like MMA, it's a good process to encapsulate everything that we need to know about a welding process, because it's got a bit of everything. It's got a bit of control and everything that we need. Okay, so MMA. Let's hope this goes through. Right. So here's a cross section of our welding process. You see this drawing everywhere. This is our version of it. What we have is a couple of different things. So we have a flux coating around a core wire, an electrode wire, right? This electrode wire is a cheap reaming steel, fairly bog standard. It's nothing really special, but the flux coating contains everything that's needed to improve the quality of that electrode once we go through the welding process. Okay, so the flux coating is really important, and we're going to talk about that. We've got our welding arc, which is that blue bit in the middle there. So that's our 6,000 degrees electricity jumping from the electrode tip to the workpiece. Then we've got the weld pool underneath that, which is our molten material at about 14 plus 100 degrees. We've got around that an evolved gas shield. So this is, as the flux melts, it gives off a shielding gas, which can be one of two types. It's either going to be carbon dioxide or hydrogen, depending on the electrode type we have. metal and weld slag. So the slag is that covering that appears on the weld metal at the end as it leaves the weld pool, and it's used for a couple of different things. It is helping remove the contamination and the rubbish from the weld, but it's also there to cover the surface of the weld to drive profile control. So it'll hug the weld metal and keep it together. It will give it the profile, it will slow its cooling rate, and then as the weld metal cools, the slag layer cools faster and contracts faster than the weld metal underneath it, so it breaks itself off and it should peel away. Different electrodes have different performing slags. Some peel more easily than others, so they don't always just peel off nicely and drop away. Sometimes we do need to hit them and clean them out with wire brushes and things like that, but they're all doing the similar sort of work. Okay, so overall that's our process as a whole. Now, if you've never seen MMA before, this is our Seabury Soldermatic system. So this is an AR training guide. You wear a helmet, you can see, you hold a torch, and it overlays everything onto our process. But what we've got here is, hopefully you can see an electrode coming down here. We've got a weld, which is all gone wrong here. But the AR allows us to overlay training aids to teach people to weld. So what we've got is the yellow dotted line on the outside is the direction we want the weld to go. We have this 4-pointed circle here, which tells us the angle of the electrode where it needs to be. So if it's green top and bottom, it means we're correct one direction. And then if it needs to be green, the other for the other direction. This bar you see here will move up and down. It'll go green when we have the right distance. So the thing with MMA is, as we weld, in my case here, because I'm right-handed, left to right, as the electrode melts, you're going to have to move the electrode in. So that bar we're seeing at the front there will constantly be telling us to move forward because it's melting away. Okay, so hopefully this should play and it should show us arcing up. So there's our weld. You can see everything sort of ploughing in. We've got our arc generating, it's producing our sparks, and we're trying to maintain travel left to right while maintaining our angles and our distance from the workpiece. Yeah. When we stop welding, we can see the really hot weld pool at the front, which is now under a slag layer, with the slag layer pulling down and cooling away to the end. Now what we'd do is we'd break that off, and then when we're finished and do that. Okay, so I'm just looking at the questions here. Will you go over the common types of electrodes? Yes, we're going to do that next. It's a really important part of the weld inspection courses, that we can identify electrode types and what they do. Okay, but all the electrodes work in the same way, so we get this bit done and then we'll show you the differences. Okay, so we'll play that one more time in case you've never really got a chance to see it in this much detail. This is why I love AR, because we get to do this. Well, there you go. So we're welding. We've got all of our things telling us how to weld, and we should be maintaining a smooth movement over. Now these electrodes come in different sizes, generally from about 2.5 mil up. Some are more common than others. But you can get them fairly big, 4 mil, 6 mil diameter. It just means more metal produced in one go. So you would route, so the first run would be with a smaller diameter, and then as you get bigger, use bigger and bigger diameter wires, electrodes. Now these electrodes, I've seen them, they can get fairly big, and of course the more diameter the electrode has, the more amperage you're going to be using to melt that material. Okay, when in doubt, about 35 amps per millimeter of wire electrode kind of gets you roughly in the right position to then tailor it from there. Depending on the electrode type, it will move left and right of that number though. But if you don't know, it gives you a number to try. Okay. Okay. So that's what we've got there. Right. So we've already talked about the arc initiation. We talked about open circuit voltage earlier on. So with TIG, that's what we've got. With MMA, that's what we've got. We have our electrode. We have no electricity flowing at the minute, but it's trying to push through the voltage. So it's got an open circuit voltage here. This one's kicking around 68 volts. Older sets are normally higher. We are constantly trying to bring that open circuit voltage down because there's a chance of electrical shock. And then when we arc up, there you go, you can see it drops down to our working voltage. Again, as the wire's melting off, the electrode's melting off, it's getting bigger, and then it adjusts and it gets smaller, and we bounce around and do that. Now what you can see this welder doing is he's welding with his right hand, he's actually going vertical up, and with his left hand he's changing the amperage. So he's feathering the amperage to be able to measure everything as we go. And we've got a palms unit on this measuring his output amperage, so we know exactly what he's done all the way through. Okay. And then when he finishes, so you can see it all bouncing away, you can see the electrode melting off, his hands getting closer to the workpiece. At some point soon, hopefully, he will finish and we'll be able to push it through. There we go. So then we can stop, change our electrode, and away we go. The open circuit voltage is back to the high end. It's trying to push electricity through, but it won't until we bring it close enough. This is one of the problems with MMA. For some reason, we've never industrialized an on-off button on the torch. So as soon as we put an electrode into the holder, the power is trying to flow constantly. So if we then touch that electrode off any of the workpieces, it will arc up and we'll get an arc strike. Okay, and arc strikes are really bad because they're rapid heating and cooling, which leads to high hardness areas, which forms cracking. We're going to talk about that when we do weldability, but it's a risk with this process. Right. Before we kind of touched upon constant amperage and constant voltage. This is what's happening with the process. So what I've tried to do here is produce a slide that connects what's happening with the electrode, which you can see on the right side, to what's happening with the relationship between voltage and amperage. Okay. The idea here is constant amperage. So as the arc moves up and down, and it gets the arc gets wider and longer and shorter, what's going to happen is the voltage is going to change. So as arc gap goes up, voltage goes up. As arc gap goes down, voltage goes down. Now you can see on the voltage side, we're getting quite a large percentage change going from 20 to 24 volts in one hit. But the amperage isn't going through the same sort of percentage change. Yeah, so we call this constant amperage. It means really no matter what the voltage is doing, the amperage, the amount of energy in the arc remains roughly the same. Right. The problem here is if you allow an erratic arc like we're seeing here, imagine getting a torch, and I normally do this on the wall in the classroom. If you get your torch and put it on the wall and hold it a distance away, you get a bright circle on the wall, right? As you pull the torch away, the circle gets bigger, but it gets less dim, because you've got the same amount of light energy hitting the wall just over a bigger distance. So when we do this with MMA, and you see when we're at the top end of 24 volts, the arc is wide enough that it's still got 200 amps over a bigger area, which means the penetration bead is going to be less because it hasn't got the same, it's the same energy over a bigger area. Then as we reverse that and come down to 20 volts, we've got a smaller arc with 200 amps. So there's more energy for the area. So the penetration bead is going to increase. So as we move from left to right and we move in and out with the arc is not only, the weld pool is not only going to be wider and narrower wherever we look at and we see the inconsistency in the profile, we will also see inconsistency in the penetration beads. And this is where, with MMA, we need the welder skill. It's the dexterity to move from left to right or right to left or up to down or whichever direction we're traveling, and maintaining a constantly smooth gap all the way. Maintain that voltage even as the wire is moving, we're walking, we're moving our arm, the pipe diameter is changing. That's the skill level in MMA. And same with TIG, when we get there, this uses the same constant amperage characteristic curve. We also call it, as you can see on the screen here, a drooping characteristic, okay? Because that constant that it's following is curved, or is a drooping curve, okay? These questions come up a lot in C-SWIP. They love questions around which of these welding processes is a constant amperage, or which of these is a drooping characteristic curve, or a flat characteristic constant voltage. In a way, you just have to kind of memorize this as rote. That process is this and that process is this. But this is why. This is why when we see welders, as we're inspecting them, going in and out, we know there's a risk we're going to have lack of penetration or lack of fusion defects. We know there's more chance of slag inclusions, because if the weld width is changing, there's more chance of grabbing the slag and trapping it in place. And we can then say to the welders, as we're doing this, look, try and maintain your arc gap, and then we'll get a better weld overall. Okay? You might not see this like on and off, on and off, on and off. You might see it that when the welder starts, it looks all right, but when he gets to the end, so he's traveled all the way across, that at the end of the weld, you're getting lack of fusion defects or lack of penetration defects or something like that. Because, of course, as he moves left to right, his arm's going to be coming up, or his electrode's going to be getting, the arc length's going to be getting longer as he moves. Because, especially when we're teaching welders, MMA welders don't like to stop and move, and you've got to get them to say, look, always be comfortable, always make sure you can reach properly and you can maintain that gap. This is where, as inspectors, we use our knowledge of what's happening in the arc pool to then drive change and quality improvements as we go through there. Okay? Hopefully that makes sense, right? If not, come back, read this bit, tie it in. Hopefully it'll get you there. Okay, so our electrode types. In the main, we have 3 electrode types in MMA. Right? We have cellulosic, basic, and rutile. These electrode types can really be characterized into applications. So cellulosics we use for stovepipe welding, vertical down welding. basics are used for high quality, good impact test requirement applications, and rutiles are your what we call general purpose. So this is kind of like just, you know, maintenance electrodes is it tends to be the throwaway term. Stuff that needs a bit of strength but doesn't need toughness, right? And then you can play with mixtures of these to get the benefits of each electrode in different positions. So one weld might have two of these electrode types being used. Okay, but in general, I think what we see in the UK in the bulk is that most people have moved to basic electrodes now, because if you just have one type of electrode, you can control it. These are basics and vacuum packs and so on, which we're gonna cover. Okay, so first covering type then we see is cellulosic covering. Now, these originally started with a flux covering that was made from flour and wood pulp. Okay, it is nowadays an industrially extracted cellulosic powder, which means its purity is quite high, its control is quite high, and it can be produced en masse. Okay, the cellulose refers to the organic compound that's in that powder, right? So when it melts and when it burns in the 6,000 degrees in our arc, it burns to produce a hydrogen shielding gas because it's organic. The organic hydrogen shielding gas has a much higher ionizing potential than argon or CO2, and therefore allows more heat to travel across the qualifying this to a degree, because we'll get lost in ions and electrons and all that, right? But keep it like this. Hydrogen increases the ionizing potential, which then increases the heat. If I increase the heat, what I'm going to do here is push more penetration into the weld. But the weld pool is a lot hotter, so it's a lot harder to control. So it doesn't look as nice. It's a lot more coarse. The weld cap tends to be kind of like doved in a bit, like sunken, because it wants to sink through the material. Now, where this is good for is for welds where we need high penetration. So in something like vertical down welding, which generally has us traveling relatively quickly, we don't get the heat input from the travel speed because it's fast. We want to get it from the arc, how hot it is, so it punches through and drives penetration into the root. The problem with this is that it's hydrogen, and carbon steel doesn't like hydrogen. It will crack, or we will have higher chances of hydrogen-induced cold cracking or hydrogen embrittlement into our structures, right? So once we produce that weld and we gain the benefit of having higher penetration speeds and faster travel speeds, what we then need to do is get that hydrogen back out. So we might have higher preheat values or post-weld heat treatment processes to help diffuse the hydrogen back out of the welds. Okay. If you're doing C-SWIP, you definitely need to know the hydrogen content levels of this. So what we generally say is above 80 milliliters of hydrogen per 100 grams of weld metal. This is really high. Hydrogen-induced cold cracking starts at anything above 15 milliliters per 100 grams. So we've definitely got to put additional controls in place to stop cold cracking, delayed cracking, hydrogen cracking. All the same, different names for the same thing, which we're going to cover when we do weldability. It's going to be a trigger. So we can look at that and go, I've got a risk of cracking. What else am I going to do? Yeah, right. Then we have our basic electrodes. So these are made from calcium carbonate. When they burn, they produce a CO2 gas, which is not as hot as hydrogen, but it doesn't have the risk of hydrogen just cold cracking. Right? Because we don't have organic compounds in the material now, it's calcium. What we're going to do is we're going to bake the electrodes. We dry them out as much as humanly possible. Okay, so up to 5 milliliters per 100 grams of steel. Now, nowadays, you'll see a lot of basic electrodes saying 10 milliliters. I think if you go back 10 years, they were all 5. They become 10 because as long as they're beneath 15 milliliters, it's all right, and you don't need the additional cost in baking them so low. So generally, we're saying 10 now, but low hydrogen, right? Low hydrogen, reducing the overall amount of risk of hydrogen cracking. Okay, now we put a lot of more alloying content into basic electrodes, which produces what we call a secular ferrite. Now this is a grain structure that has good toughness values in carbon steel, and therefore when we have cryogenic sort of materials, I say cryogenic, not that low, like -10, -20, -30, -40, the secular ferrite is going to work to make sure we've got toughness values at that level. And it's going to give us the output. But of course, a higher alloying content, a higher overall cost of the electrodes because there's more things in it. Okay. We have sort of 2 ways of dealing with this. The old school way is to bake the electrodes. So your electrodes would be loose. You'd put them into an oven, bake them at like 350 degrees, get for so many hours. The get out of jail here is follow manufacturer's recommendations, and then take them from the oven and put them into quivers that each welder has, above 100 degrees, 150-ish degrees, something like that, keeps them dry as you use them. Now, the main drawback of that is if every welder needs a quiver, every group of welders needs an oven, dried and controlled correctly. You need to make sure you've got power everywhere. Overall, there's a high cost to that. So what we do nowadays is we buy them in vacuum packs, which are sealed units which have been baked and dried by the manufacturer. They come to us. We get them out of stores. We write the time that they've been booked out. We open the packet and we have a small bag, of a couple of kilograms of wire that we use, and then whatever's left at the end of our time frame we get rid of. Time frames depend on humidity levels. Generally we say a shift, so 8 to 12 hours, and then we bin them, and then we get a new pack and away we go. So as inspectors, that's one of the things we're looking for during our inspections is what vacuum packs have we got on site, how long have they been there for. You'll see them, they have like little labels on them that the manufacturers produce for you or the storeman to write in, and then you can check against that and make sure things are okay. In my experience, the electrodes nowadays, especially from the big manufacturers, the ESABs, the Oerlikons and whoever, are produced that they give decent resistance to moisture pickup, even the basics, right? But we call these hydroscopic, is one of the main words here, which means as they draw in water from the environment. So if you're in somewhere fairly humid, the time frame is going to be less than somewhere that's fairly arid. Okay. Right. The last one then is our rutile electrodes. Rutiles are a general purpose. They have a decent amount of hydrogen in them. It depends which make you're using. I'd say 15 to like 30 as a range. We're not really using these for hydrogen critical areas, but they arc up really nicely. If you're going to learn to do stick welding, you should really start with rutiles, because you'll get the movement, they arc up nicely, they run nicely, the slag peels off more nicely, but they don't give us good toughness values, but decent strength. So if you're using it, you're making a fabrication and it's only ever going to be warm, above 0 degrees, there may be no issue if you're using hydrogen electrodes, rutile electrodes in your procedure. But we follow the procedure and we do whatever it says, So general purpose electrodes, medium hydrogen content, general purpose. Okay, so that's our 3 electrodes: cellulosic, basic, and rutile. Cellulosic, high penetrating power, high hydrogen content. Basic, high toughness values, low hydrogen content. Rutile electrodes sit in the middle, general purpose electrodes. Okay. Now we need to know how to identify these. Okay, here is, again, if you're doing C-SWIP, you're going to need to know the BSAN classification and the AWS classification. Okay, they're different and they talk about different points, and these are where the exams for C-SWIP definitely try to make sure that you understand the difference. I don't want to use the word trick you, because that's not what they're trying to do. What they're trying to do is make sure you know the difference between which one is asking for yield strength, which one's asking for tensile strength, because there's a difference in European and American measurement systems. Which one is measuring is a newtons a millimeter squared, and which one is measuring as PSI, all this type of thing we've got to be careful with. Okay, so the BSAN 2560 gives us an example like this, right? So the first letter is E, so this means it's a covered electrode, which tells us straight away it's an MMA electrode. ER is a bare wire, so if you look at an MMA, MIG-MAG or TIG, it'll say ER70S, because that's their classification. For stick welding, it's always an E. Then we've got the next here, 42. It could be a couple of different numbers, 35, 42, there's a lot of different standard numbers here. But this is in the first one for us is its yield strength. And what we do is we just add a 0 to that. So 420 newtons a millimeter squared yield. Okay, that means that I can look at that electrode as a welding engineer and go, well, I'm welding S355, that's a 420 electrode, I should be matched on my yield strength from my weld metal to my base material. Very quick, easy way of being able to pin European grades of steel when they say S355, which is a structural steel 355 newtons a millimeter squared yield, to a electrode, right? I can get tensile and elongation from that number, but what I have to do is go to the standard 2560, find the table, look down for 42, and then it'll tell me it's 420 millimeters newtons a millimeter yield. It's got a tensile range, and it'll give a range of tensile strength, and then an elongation of this value. Okay, nobody's expecting you to remember the tensile strength and the elongation. but I need you to know where it's coming from, okay? And you should be able to tell that it's 420 yield because you just add a 0. If it's a 35, it's 350 yield. If it's a 65, 650, etc. You know, just add a 0 to it. And it's always in yield for BSEN standards, okay? Never tensile. So in a multi-choice, they will say things like, oh, is it 420 newtons a millimeter yield, or is it 420 newtons a millimeter tensile? It's all, a lot of people make that mistake. Okay. Then we've got toughness values. So this 3 means that we have a toughness test applied to this electrode, this weld metal, and it's been tested at -30. So this number is always a negative number. And we can then again look at our base material and say, oh, well, I'm welding S355, it's been tested at J2, this exceeds that requirement, so that should be all right. Okay. We've then got a letter, which could be one of a couple of different, 3 main letters and four letters, right? So this is our flux covering. B is for basic, R is rutile, C is cellulosic, and RR is a heavy rutile. So a rutile with iron powder in it, okay? Makes it nice and easy to identify the electrodes. And then we can tie to what we learned before to understand why each of them would be like that. So of course this is a basic. It shows very good toughness values, -. We then have numbers for weld metal recovery, welding position, and electrical characteristics. In the main, to worry about this too much, you would go to the standard for these and pull it out. The welding position just it's a chart. You go down, you come to 2, and it tells you what welding positions it's in. Same with electrical characteristics, DC, negative, DC, positive, AC type of stuff. And then the last one is our hydrogen content. So this is saying that when manufactured, what we're doing is or dried, we have a hydrogen content of 5 milliliters per 100 grams of steel. Okay, so that's kind of how our EN classifications work. A hell of a lot of information, which is brilliant for me as a welding engineer because I can see everything I need to see, right? This number can be subdivided again. So we've got mandatory, so the standard says you have to give these, and we have optional. Now, the manufacturers don't kind of split it, they just put everything on because they don't then need to produce 2 sets of packaging for everything. So when we do to 2560, you tend to get both the mandatory and the optional, okay? And we get that. Hopefully that's okay. Right. Then we've got the AWS classification. So here we have similar but different, and this is where the exams can trip you up. Okay. So E, covered electrode again. That keeps us right. R70, that first set of numbers, is now tensile strength. In this case, we're showing it in KSI. So this is 70,000 PSI tensile strength, which is not the same as yield. When we do mechanical testing in a future session, we'll go through the difference on a tensile graph between tensile values and yield strength values. They're nowhere near the same, right? So don't get them confused. The 1 is the position, and the 8 is the flux covering. Now, when we talk about American grades of electrodes, we often would say, we'd call this an E7018. We put those last 2 numbers, the 1 and the 8, together, but they're not. They're actually separate. Okay, so it could be a 2 instead of a 1, right? Then you've got your number. So the general ones tend to be 10. So it's 0, 1, 3, 5, 6, 7, 8. Okay, that covers there. Then we've got some additionals, again, some optionals. So low impact test requirements, hydrogen content, and moisture absorption tests. Again, if you're doing this for C-SWIP, it's only really them first 4 we're looking at. Okay, don't worry too much about the last stuff. Okay. So how do these compare to each other? So what we've got is we've got AWS and EN, so identification of fluxes. So you can see on the AWS here, it's that last digit we're looking at coming down. So the 0, 1, 3, 4, 6, and 8, right? This is how they pull across. So what we would call a 10 or 11 is cellulosics. Your 13 and 14 are your rutiles. And then your 16 and your 18 are your basics. So your 6, 8 basics, right? You very likely could be asked to compare the two in a question. Which of these is a cellulosic? Which of these is a basic? Or, you know, a 80-16 is what? You need to know it's basic, and so on. So this type of chart you need to commit to memory to be able to get. You need to know it generally. Okay, and understanding that, I feel that it's easier to talk about electrodes using the AWS classification, but it's better to engineer with EN classifications because we get the information in a much more accessible method for welding engineering in EN, but we can talk about it much more easily as an AWS. So you need to know both and be able to jump between the two and understand that there is limitations for knowing if they're exactly the same. So how would I know if a 70-18 is the same as a 35 basic in EN? You wouldn't. Straight away, you'd have to go and check the EN, look for the tensile value in the standard, and then try and map over. It's not just a very quick check, unfortunately. Okay. Right. Okay. So that's MMA. That is kind of the very quick overview of the absolute minimum you need to know to be able to capture to deal with that. And that's quite a lot of stuff, isn't it? So we've got how we produce the welds, how we produce a shielding gas, and how the shielding gases change depending on the flux covering. You've got your free flux covering types. You've got your applications of them and the identifications coming down. Okay, when we're going to cover the types of defects in another session under the defect session, but there are going to be certain defects which are more applicable to MMA, like slag. Pardon me, because it produces slag as a whole, right? I've got you guys booted up on my phone so I can see the chat just in the general stream. So let's have a look. So, are there any questions here? The comfort money. I did my. So let's just make this small here. I did my 3.0 and have a quick question. In the plastic test sample, there were slag inclusions. The slag inclusions were quite deep. Would you class it as underfill? All right, yeah. So we are going to cover this when we do welding defects and things that I think are good for you to be able to think about in your practical tests. But if it's on the sidewall and it's going deep, C-SWIP like you to class it as almost potentially 3 things. So slag inclusion, a lack of sidewall fusion, and underfill, because it's 3 different things in one area. So Mohammed says yes to slag inclusion underfill. Yeah, I would agree. Potentially lack of sidewall fusion as well, depending on how the defect presents itself. And then and then Brody's got possible lack of sidewall fusion as well. Awesome. That's everybody's actually given good answers there, and I agree with the overall consensus of the group. The thing to tie to what we're doing here would be that, remember, it's only slag if it's a welding process that is going to give you slag. So if they say it's MMA is your welding process, yes, it's slag. If they say it's GMAW or MIG-MAG, it's not going to be slag, okay, unless it's flux core. But so it might be silica or something like that. This was more of a thing when you had macro sections to do at 3.1 until they got rid of them, because the macros would split between stick or MMA and MIG-MAG, and the defects inclusions would either be slag or silica, and you had to kind of know. But always keep in mind which welding process you're using to be able to drive that out. Okay, I'm going to stop there for a few minutes just to go and get another cup of tea, because I've been talking a while, and give anybody a chance to ask any questions while I've been talking, or anything you think you might want to cover on MMA. Give me, I'll put a counter up. We'll have 15 minutes quick break, and then we'll come back and continue. Okay? I'll catch you in a bit. I've got it open on my phone, so I can see, like, as a viewer, so I can see, let's see if I can put it on. And then hopefully that's all working, and it's got a back soon up now, hasn't it? Can you see that? Yeah, but right now, you see the screen and see the back soon. Okay, hopefully that's us back up and running. Good for a quick cup of tea and a break, but we'll get there. So that's MMA. Like I said, it's the big drive for C-SWIP and how they, in particular C-SWIP, how they build their exams, because they can ask a lot of questions and stuff. So the more that you can make sure that you understand that process, the more likely you are to be able to pull lots of different positions all the way. So what MMA allows us to start to do is to say, right, well, we know MMA has hydrogen potential over these 3 different electrodes, right? Well, if we now look at what is the worry about hydrogen, we can pull in hydrogen just core cracking. We can pull in preheat. We can look to see how the effective mechanical properties for alloying content from the alloying body do we put into the flux. What are all them alloying bodies? So in the next stage, when we do weldability, we will be coming back to MMA because it gives us that nice through sort of put in how it all starts to jive together. Okay, but the next one we want to do is to do MIG-MAG. Now we will hit the normal statement, which winds a lot of people up. It's either you get really upset by this or you really don't see why it matters. And I kind of go on both sides of it, depending on whether I'm making a mistake or not. And it's the difference between MIG and MAG. Okay, they are different. The thing with the industry, though, is that we just call everything MIG because it's easy. We don't have to think about it, but it's not technically correct. So MIG is metal inert gas, MAG is metal active gas, and the 2 big things here are the types of materials we're welding. So before we do anything else, we just want to say MIG is for aluminium, MAG is for steels, whether that be carbon steel, stainless steel, Inconel, don't care. MIG is only aluminium. That is a line in the sand technically, so we want to make sure we get that, because there are famous questions, as there's a lot of everyone know, like, which of these processes cannot be used for carbon steel, and it'll say TIG, MIG, subarc, plasma or something like that, and people look at it and go, well, all of them can be used for carbon steel. No, right? MIG is for aluminium, inert gas, 99% argon is for aluminium only. To weld carbon steel, we need to have a active gas constituent. Normally, it's a 20% CO2, but it can change. But that's a standard one, which is an argon CO2 mix, and that gives us more energy because carbon steel has a higher melting point than aluminium. Okay, we've got to get that one nailed before we do anything else. Okay, but the little tagline here, same process, different consumables, is the same. These are the same bits of equipment, just the gas or the filler wire we're going to use is going to be different. Okay, right. So what do we have? The system. And what's going to happen here is that as the electricity moves through the electrode wire, it's going to come to the end of the wire and arc up over there, and that's where we're going to have our arc again 6,000 degrees, and that's going to push like that. We will then shield the area with a shielding gas. If it's MIG, it's 100% CO2. If it's MIG, it's 100% argon. If it's MAG, it's got a CO2 addition, right? And then we can push from there, right? the electricity is moved into the electrode wire by our contact tube, which pushes through, and the electricity and is normally a copper based, a brass based fitting, which can wear as the wire moves through it, especially if we're using quite a hard wearing consumable like an Inconel or something like that. Okay, that can contaminate the weld pool, which we've got to be careful with. So we do have to start swapping out fittings fairly regularly. Okay, these don't last forever. And our gas nozzle is pushing our shielding gas down into place. If we look at it as our weld pool here again, in our AR, what we can do is we can start and we see our arcing up, and we have the arc being produced from the end of the wire. It's always good to see at least a little bit of the wire at the end. We build along, but the thing here with MMA, what happened is we only had an amount of electrode that we could weld with. By moving to MIG-MAG, we have a 15 kilogram spool of wire which continuously feeds, so we can continue to weld as far as we can. Okay, it means we have reduction in stop starts. We should have an overall improvement of process efficiency. So with MMA, we're looking about a 30% efficiency, which doesn't allow us to really play with very much. Okay, but with this, we can automate it and improve the efficiency of a process, so we can fill much thicker materials much more quickly. Okay. Right. So, like I said, we've got a difference between MIG and MAG. So we've got a metal inert gas and a metal active gas. So the inert gas is usually 100% argon. I say 99.99% argon, but you can mix it with helium. The helium gives a lot hotter arc, but the problem here is that the helium is a lot more expensive, and it's expensive to buy, and you use a lot more of it because it's a lot lighter than argon, so you need to use it at much higher flow rates. So it's an expensive gas which you use more of. So in a lot of senses, people have tried to move away from helium. The cost of helium on the market goes up and down quite a lot. Helium is a strategic gas for a lot of different things. It's critical to medical equipment, MRI scanners and things like that, which means that countries who produce or capture helium may decide not to sell it on a given political state, and it can go up and down in not just cost but also availability. So if all of your welding procedures are qualified using helium in order to get productivity, and then you can't get helium anymore, you don't have a weld procedure. You've got to kind of requalify it. So this happened a few years ago when America decided to kind of choke off the supply of helium to get the price up. And a lot of people moved and just went back to argon, lived with slightly slower welding speeds, but known they can get that consistency in their output moving forward. Okay. Right. Active gas can be 100% CO2. The problem with using 100% CO2 is it's very violent. As it arcs up and produces the energy transfer, it's just a bit crazy. So you get lots of spatter. The weld pool can look a little... violent is the only word for it. So it's best to have an argon mix. 80% argon gives us a really good stability with a bit more power in the overall arc from the CO2. Okay, we need 80% argon in order to produce spray transfer, which we're going to talk about as well. So 100% CO2 will only ever work in dip. It can't do spray. which limits the use of CO2 as well as a pure shielding gas. We have a lot of different shielding gases, and ISO, we have it's our own standard for it. So ISO 14175 gives us a load of different shielding gases along with the colours and how the bottles are inscribed or coloured. These changed a few years ago, so I don't know if you go back when I started my apprenticeship in 2003, they were all different colours. But as Europe is solidified their output to be one unit, it's become a lot more normal like this, right? So there's lots of different types. Again, we would fall back to the Weld procedure, which would tell us the shielding gas we're using. In some cases, shielding gas type and make are essential variables for different clients, so we've got to be careful with this and making sure we don't change the composition. And one of the biggest things we see is that the different gas manufacturers call their gases different things, and even for the same essential gas have a different mixture, which then affects qualification ranges. So we've got to be careful when jumping between one manufacturer to another. I don't know, from BOC to Air Liquide or something like that, or Air Products, they might all have different variations of gas. Is it MIG or MIG? We've talked about this a lot. We drive this home extensively because we have the difference in exam questions on what is MIG, what is MAG. So make sure we're happy with that. Right. Effective shielding gas on weld profile. We saw this in MMA, where we could see the difference between a hydrogen shielding gas with cellulosics and our basic with CO2 gas, where one would have more penetrating power than the other because of the type of gas. So here it is in MIG-MAG. Argon produces this finger-like profile, okay, where CO2 produces a more domed-like constant melting and around. And that could cause you issues if you're looking for things like, why am I getting lots of excess lacquer sidewall fusion or something like that. The profile of the welds, especially in deeper welds, is something we have to account for. So you can see that by mixing argon and CO2 together, we start to get that deep but wider weld, which means we're more likely to catch as many different things as possible, okay, and make sure we capture the full penetration and cross pen and stuff like that. Okay. Our welding consumables, so if we look back at MMA, we were stuck to welding electrodes, which are about 200-300 mil long. Now having aluminium, I'm reading the screen, by having spools like what we can see here with the aluminium wire spool there on the left, we can make much more potential for welding. So we can keep welding until that runs out. That is going to be hundreds of meters of welds before technically we need to stop. We'd probably just run out of physical things to weld and have to restart before we ran out of welding wire. The way we produce the weld transfer, so we make the metal move from the electrode wire to the workpiece, comes in a few different types, okay? We generally call these 4 modes of transfer. So we've got spray, globular, short circuit or dip, and pulsed, right? In the main, though, we generally work on having 3 modes of transfer and 1 non-desired mode of transfer. Okay. Now the non-desired tends to be globular nowadays. It's an old form when we didn't really have pulsed, we would use globular to try and find a halfway house. But now we have pulse, we can kind of forget about globular and just work on spray, short circuit, and pulse modes. Okay. What happens here? So starting with the first one, dip. This is a motor transfer which has relatively low amps and relatively low volts. So the heat input and the amount of energy in the arc is not huge, right? What this means is that we can see on our picture here that an arc can be produced between the end of the wire and the workpiece, and we have an arc. But there's not enough energy there to melt the wire. So the wire is going to come down in the arc, not melt, and hit the surface of the workpiece. At that point, we're going to cut the arc off. We're going to what we call extinguish the arc. Right? That arc now becomes a short circuit, which is like a fuse in the weld. And the fuse, as the wire, will heat up until it snaps. We reform the arc because there's now a gap, but there's not enough energy, so the wire comes back down, touches the workpiece, and goes on. So that's what we're about to see, right? So we have an open arc. Yeah, I'll get the video moving, and then we should be all right. So you see, open arc, close, snap. Open arc, close, snap. Open arc, close, snap. So that's the dip transfer. In the UK, we tend to call it dip. In mainland Europe, we tend to call it short circuit. So it's that pushing and snapping, pushing and snapping. What are the benefits of this? Well, one of the biggest ones is that I don't rely on anything to transmit the wire, the molten metal, from my electrode to my workpiece. I'm forcing it in every time, okay? Which means I can do it downhand, I can do it overhead, because I'm basically painting the weld in place, okay? One of the downsides of this is we're at relatively low amperage and voltage, so the heat input overall is low. What that means is we're not going to get a lot of penetration, and we run the risk of lack of fusion defects, especially in thicker materials which need more energy to melt. Okay, but on thin materials, because we don't have a lot of energy, it's easier to weld. So we're doing thin gauge sheet, cars, thin gauge material for more aesthetic-y stuff. This is great, okay, because there's not a lot of heat there to blow the steel away, right? So dip transfer, great for all positions, but gives the risk of lack of fusion type defects, okay? And in its cheapest form, we see this in places like car garages and stuff, because they can use 100% CO2, which is a cheap shielding gas, because they don't need spray. Yeah. Now, every time that wire breaks and disconnects and reestablishes the arc, we have a removal. We have an explosion of energy, right? Which means that we're going to get spatter leaving the workpiece all the time. Okay, and we have to really start to address that, because if we just use dip transfer, we're going to get a lot of spatter. We're going to have to do a lot of cleaning before we do additional paint and works or finish the job. Spatter in itself is not a welding defect, but it will affect the next application. So it'll affect the application of NDT. It will affect how the painting system adheres to the surface and things like that. So we need to reduce it or get rid of it altogether, right? So what we have is a thing called inductance, right? So inductance is used in dip transfer within MIG-MAG welding, right? So what we've already identified is that the wire is going to make its way through the arc, right? There's not enough energy to melt it, so it'll form a short circuit. And at that point, we've got an amperage level. When it forms a short circuit, the amperage level is going to peak because it's a short circuit, so it can run more easily. It increases, right? It then, oh, that hasn't worked. There you go. It then, come back one there, sorry, getting ahead of myself on the slides. It then peaks, and when it breaks, the amperage drops back down, and we get spatter flying all over the shop, right? That peak we're seeing here is too much. It's not needed. So what we do is we add inductance into the system, which is a way of choking off that peak. So instead of it peaking up on the solid line that you can see, we pull the electricity to the dashed line. And by reducing that peak, when it explodes and we get that release, we get less spatter. Okay, so that's inductance. It's a way of reducing spatter in dip transfer. Right. The next one we've got is spray transfer. Spray transfer, the wire, the electrode wire, is never going to make it to the workpiece. So what happens here is we have more amperage to melt everything else in the arc as we go, right? So greater than 220 amps, greater than about 26 volts, and we need at least 80% argon to make a stable arc to allow this to happen, right? What happens here, there you go, is the arc is hot enough to melt the wire at the end, so we get fine droplets of material leaving the arc and moving, making their way across, right? So we'll keep playing that. There's more amperage here, so there's more heat, which means we can't weld thin materials with it because we'll just blow it away. But in thick materials, we have less chance of lacquer sidewall fusion issues. The other problem is when we go to work overhead, though, we're now relying on gravity to pull them droplets down over the arc. There is a small amount of magnetism through Lorentz forces, but it's not enough to overcome gravity. So if we try and do it overhead, it'll just fall back down on top of us. So we restrict the welding positions that we can weld in with spray. Generally we say PA, PB and PC. Potentially PD, but it's getting more difficult. But PE overhead, it's just not going to work. Okay. But reduced chance of lacquer fusion when compared to dip transfer, but we can't do it on thin materials. Right. I want to come back to this in a second here. So next we want to talk about a self-adjusting arc. Okay, the self-adjusting arc is driven by our flat characteristic curve. Now this curve is going to connect voltage and amperage in a way that the burn off rate of the wire is going to be affected. Okay, so as we now try and move our torch in and out, you can see that the end of the wire doesn't change. So the arc size remains consistent. Now this is a thing because if we go back to MMA, when we did a constant amperage source, what was happening is we were welding along and the weld pool was changing diameters, which was then changing the penetration bead. With MIG-MAG, or this constant voltage characteristic, as we try the arc, the voltage affects amperage. So as we try to pull the arc away, the voltage increases, which drops the amperage, which means the wire moves closer to the workpiece. And then as we push it closer, the voltage goes down, which increases the amperage, so the burn-off rate of the wire increases because there's more energy. That is an instantaneous feedback. So as you try to move even a tenth of a mil, it instantly corrects and allows the wire to move forward or backwards. And so that end of that wire never moves, which means we get more consistent welds with MIG-MAG than compared to stick, because we have the arc itself adjusting itself as we move along within reason. And actually we can move quite a distance and have this effect happening. Okay, so this is a self-adjusting arc, which is our flat characteristic constant voltage. Okay, so if I play it on the video here, you can see as we're welding along here, we can pull that electrode, or try to pull the electrode quite far, and it continues to work quite well. Yeah, and we pull it off. Okay, so this allows us to industrialize MIG-MAG a lot more than we can MMA. Right, we talked about that. Right, then we've got flux core. So all flux core is taking the MIG-MAG setup and changing the wire that we put through it. Okay, so MIG and MAG are both solid wires, but it's really the gas that's changing. It's either active or inactive gas. Flux core, we can have that play with the gases, but we also change the electrode. So we were saying with MMA, one of the problems is it's 250, 300 mil long electrode, which means we've got to weld and stop, change everything, take the slag off, reset up, weld and stop. So our efficiency is about 30%. It's terrible. It's really expensive. But we get all of this alloying content support to make the weld better, get slag, which can help deal with profile, slow cooling rate, lots of advantages. So really what we want is MMA, but industrialized like MIG-MAG. That's flux core. So what we do is we make an inside-out MIG-MAG wire, MMA wire, so the flux is on the inside of a wire, right? We have two versions of this. We either have what we call outer shield or inner shield. So outer shield looks very, very much like MIG-MAG. The wire we use has alloying content inside the core of the wire, but not really enough to generate its own shielding gases, right? So we still need a separately applied shielding gas. Inner shield has a lot more stuff on the inside of the wire, so it can produce its own shielding gas, and therefore you don't need an external gas bottle, and the torch looks very different, okay? Because it doesn't need the gas supply equipment around it. For a while, a lot of people tried to go to inner shield, but one of the major outputs of it is huge amounts of shielding gas fume. It's like clouds as you're welding. Your workshop fills up with harmful fume. Everything gets covered. It's just not worth the hassle. You need a lot of fume extraction. So a lot of people have gone back to outer shield, which has the benefits of MMA, but doesn't have the excessive fume gas that inner shield has. And we kind of play with that as a whole. And over the last 10, 15 years, a lot of work has gone into filler wires for outer shield, so they just get better and better all the time. Initially, they were really difficult to route with. Now you can route with them and fill out completely. And we're getting something that is just really taking over the world. I think in the main what we see is TIG for routing and then flux core for everything else, you know, and in that I can see us moving continuously in that direction as those fluxes get better and better. Okay, but one of the drawbacks with this is with MMA we can dry the electrodes. We can, you know, make sure they're rebaked and they're where we need to be. With an outer shield flux core coil, it's dry when it's made, and then we open out the pack, but water can get in, and we can't really stop that from happening. So some places what they do is when they finish the shift, they take the coils back off the machines, put them in a bag, put some silica gel in there to keep them dry inside, and the next day they bring them back out and away they go. It can get quite extreme to gain control over a system, but overall it's good. They're good to use. And I don't like saying this, but I'm going to say it anyway. MIG-MAG flux core is less skilled than MMA because you don't need the dexterity. You're relying on the self-adjusting arc, the constant voltage profile, to do a lot of the work. Therefore, you can industrialize a system a lot more easily. Okay. Yeah, we talked about all that. Right. One of the interesting things is increases in deposition rate between solid and hollow wires. So if we have a mag weld, carbon steel, and we have a solid 1.6 mil wire, what this table shows is deposition rate, so the amount of weld we produce per hour. So we measure it in kilograms an hour at different amperages along the bottom there. You can see the higher the amperage, the more metal we produce because we get more burn off rate. Okay, that's kind of standard, and that keeps us right. Now, what do you think will happen if we change to a hollow wire? So the outside diameter is still 1.6 mil, but it's now hollow. Will we get less metal or more metal? I don't think I'll get a chance to see you make comments on it, but I'll kind of pause for a minute in case somebody wants to take a stab at it. Well, what happens is that the hollow wire produces more deposition, like that. Okay, now why would that be? Because there's less metal per cross-sectional area. How can it produce more? Well, what's happening is, because there's less metal for the same amount of amperage, the machine has to put more wire in order to maintain the arc, because the burn-off rate is higher. So the filler speed is higher on a flux core than it is on a solid, and therefore produces more metal, right? So not only are we getting the benefits of having a flux, alloying content, slag, which deals with profile and all that type of stuff, we're also getting more deposition. So we're filling joints faster, and therefore the economy of the welding process gets better. Even though you might be spending a little bit more money on the wire, look at that performance. You know, at the top end here, we're talking potentially like 4 or 5 kilograms more an hour. That's a lot of weld, you know, and it's what we've got to keep pushing through. So you can see why we move more to flux core than not. Yeah, so here is it, kind of just like me trying to give an example, so you can see the cross-sectional area for a solid wire is going to be more than something for a hollow wire, and you can work that out and work out that change and why the ratio between cross-sectional area to amperage will have to be greater. Okay, right, so that's MIG-MAG flux core. So the thing I need you to take from this is MMA is great, but it has a really low efficiency. What we want to do is increase the way in which we can really hit the productivity requirements of general industry nowadays. So we want to move to MIG-MAG, but we lose the benefits of MMA. So moving to flux core then gives us the benefits of both worlds, yeah, while almost reducing the skill level required and making it even better from an industrialization point of view, because more people can do it faster. Yeah. You have to remember the difference between MIG and MAG. There is always a question about that. It's just the famous question. And knowing the difference that MIG is for aluminium, MAG is for carbon steel, or steels in general, is where you want to be. Okay. Yeah. You need to know your modes of transfer. So we've got 3 modes of transfer and 1 non-desired. So dip, spray, and pulsed. We didn't really do pulse, but we'll do it in another session. Okay. And then your dip is for thin materials, all positions, but a higher chance of lack of fusion. Your spray is for thick materials, restricted in position, because we're now relying on gravity to pull the material over. Okay. Right, last one for today then is going to be TIG welding. That's going to mean we've done quite a decent live stream, and we can catch up on anything in the next session, right? But TIG. So the thing here is that it's excellent, and I would say that because I'm a TIG welder, but it's really expensive. So we have to really, at what point do we need the quality? When can we get that with one of the other processes? And you know what? Every process is capable of producing 0 defects. Absolutely it is. Just somehow it's easier to do it than others. Okay? So TIG, because of what we're going to have to do for cleanliness and skill levels, we should overall see better quality welds. But we should, maybe before we start, let's hit that term. What do we mean by quality? Is quality that it's always 0 defects, or is it that it just meets the requirements? All right. Why would you want 0 defects if it doesn't matter? We've got to engage with that. We'd all want 0 defects and everything, but there is a cost to that all the time, right? So TIG welding, we say highest quality, and it is, but is it always required? Okay. Right. Okay, so TIG welding, what we've got is we've got a torch which has a tungsten electrode within it, right? This tungsten, this longer a bit, yeah, is what we call a non-consumable electrode. So all of our welding processes up to now have had a consumable electrode because the wire has been a part of the circuit as we go through. In TIG, we remove the need for the filler wire to be in the circuit. So we have a non-consumable tungsten electrode and a separate filler wire. Okay, that has benefits, a lot of good benefits. Now that tungsten can be a couple of different types. Right? Some more common than others, and they all have pros and cons. Okay, probably the best overall electrode, if you were to ask me, is a 2% 48 electrode. Okay, so these are the red tipped electrodes. These are brilliant because they have very high current carrying capacity. which means they can take more amperage for longer without melting. Does anybody know what the biggest problem with foriated electrodes are? Because there is a fairly major issue with them, which has got a lot of people concerned, and we have to look at different ways of dealing with them. I'll give it a second, so you can just have a think about it more than anything else. The biggest problem here is foria is radioactive. Now within the electrode, it's fine, no problem at all. It's your skin filters it out, and we're all good. The problem is when we go to sharpen the tip of that tungsten, and we allow the tungsten dust to become airborne. We breathe it in, bypasses our skin, goes into our lungs. Now you've got a radioactive substance in your lungs which is trapped, which has the potential to cause cancer, right? In the States, that's actually been won in court, so it's got a lot of people more worried and more thinking about it, that, you know, people could sue for cancer causing things. So now, especially in the UK, we push a lot for confined sharpeners. So these are items where you put your tungsten into a collet holder, you put it into the machine, it's all sealed, so the dust is never airborne. It normally goes through like a water trap or a filter, and it's all kept. But then you have radioactive waste, so it has to be disposed of correctly in accordance with the requirements of the local legislation for it. Okay, but that's some of the best electrodes. So we can swap that out with different types. Okay, so the foria is an alloy. The other alloys are serrated and lanthanated and zirconiated, right? So they all have different abilities and different current carrying capacity. Some are better than others for being either DC or AC. You can see on our screen there, there's a little bit of see it on the screen there. I'm not even sharing my screen. I should be on here. Nobody's saying, right? So yeah, you got your tungsten and you've got this chart. We'll go back to it. There is down the welding modes, you can see AC, DC, and so on. You've got your different colours of electrodes and the different alloying contents, right? So foriated is red, 2% is red. Most of the common ones are your grey, your serrated, and zirconiated are fairly common. Pure tungsten is possible. It's green. It does okay, but at relatively low amperage values. Okay, it has to be low amperages, and or it just melts, and then we get tungsten inclusions in our jobs, right? We have a collet around the tungsten which connects up the electrical current into the tungsten. We have normally a ceramic cup which helps push the gas in the right direction. These are normally ceramic, but you can get see-through ones and all that. I don't get the see-through ones. Some people love them. I don't really see the point. We have a heat shield that stops the heat or tries to reduce the amount of heat transmitting back up into the torch. You got your torch body, your tail, which can either be stubbed or long, depending on how long your tungsten is. Right. So what's going to happen here is from the tungsten, we are going to strike an arc. Right. Get this working. Right. When we press the button, what happens is we push shielding gas through the area to protect it. We then strike an arc from the tungsten electrode into the workpiece. So we get our arc again at 6,000 degrees. We get the resistance, which creates our weld pool, and we drive forward like that. Okay? That's all you need in TIG. So unlike with MMA and MIG-MAG, where you needed an electrode filler material in the pool, we don't need that. So we can just melt base material to itself in an arc and not add any additional material. Okay, if we're doing it like that, we refer to it as autogenous welding. So that's welding without filler material. This is used normally when we have a really, really thin material, yeah, where if you were trying to push a filler wire in, the filler wire would need melting, so that would take some of the heat, which would potentially blow a hole in the material, or just the action of adding filler material would disturb the pool enough not to make it weldable. Okay, so you can fuse through autogenous welding. Okay, it's used a lot in tack welding, pin tacks, skin tacks they're called, which can pull that together. Okay, right, but we might want to add a filler wire. Our filler wire, as we add it, right, filler wire is really important because we're really using a matching filler wire to what we're welding, and the selection of TIG filler wires is a lot more restricted than it is for MMA, right? So if you're welding a 316, you tend to use a 316 wire. These come in 1 meter lengths and are a lot more expensive because of how they're packaged and what you do. Some base materials, you can't, there's no filler wires produced for it because they're just not commercially viable. So what I've done in the past is actually on a guillotine cut sheet strips of base material to use as filler metal in the process. I once had a job welding platinum, and that was one you had to do. You had to cut it all out and then fill it in. But then we add the wire and we go, but we can choose how much wire we want to add, which again adds to the level of control we have in the process. Do I want to add some more wire or not? A lot more wire or just a little bit? And we can play with it and have that control. And that's the big thing about tungsten inert gas, is the control we have as a welder. Okay, so then we can just keep adding that in, and away we go, in and out, getting that nice ripples, get it all looking good, and away we go. Okay, now some torches are water cooled, some are air cooled. Higher amperages, water cooling is better because these torches can get very hot. Okay, right, so if we look at it in our AR again, so what we've got here is we've got our arc being produced between the tungsten and the workpiece. We've got our filler wire being added separately in depths into the arc. The big thing here is our ability to see the weld pool. In MIG-MAG, flux core, MMA, that's pretty much non-existent. You kind of pointing and hoping, but with TIG we can see the pool. We can see the width of the pool and get it to where we want it to be and maintain it. We'll know if we need to speed up or slow down to maintain that diameter of weld pool and keep going. Okay, so this is why we live with a lot slower weld speed, and not just in travel speed but also deposition rates, because of the control. If we don't need the control, we can use MIG-MAG flux core. If we do want it, this is where we use. So where would we want to use this? Industries, high-end industries, there's reasons we live with the higher cost. Okay. Right. So the arc initiation of what we're doing here, what we're going to have, so every machine will have a sketch on it that looks pretty much like this. Okay, so there's an amperage sort of top end and a time moving along the bottom. What happens when you click the button? You get your first section, which we call pre-gas. So this is how long does it take for it starts pushing shielding gas out before we get an arc initiated. Right? We put this in seconds. Right? Then in some sets we can set what we call a pilot arc. So this is a very small amount of amperage that comes out to produce an arc that's not sufficient to create a weld pool. But this allows you to set where your position is and make sure you're in the joint and where you want to be. Okay. We can then slope up the arc. So you can see the arc is then getting bigger off the weld pool, right? And what this does, it stops thermal shock into the tungsten. So we don't go from 0 to 100 amps because that might split off some of the tungsten off the tip into the workpiece. What we're going to do is slowly power it up. Again, we set this in seconds. And then we get to our peak current, which is our weld current. And then when we're finished, we can come the opposite way. So we can slope it down. Slope down here is to do with crater cracking, which is a welding defect which is caused by a large weld pool solidifying too quickly. And we'll do that when we do welding defects, but if we slope it down and make the weld pool smaller and smaller, when it does turn off, the surface area isn't enough to cause a crack. Okay, so that's what slope down's for. And then you'll have your potentially a pilot arc again. You don't always have to have that, but some do. And then you have your post gas time, which for reactive materials like stainless steel, titanium, stuff like that, you leave the gas on so the whole of the metal cools in an inert gas so that it's below, say, 400 degrees before the oxygen gets to it and it doesn't oxidize. If you're doing something like stainless steel, this means that when it stops, it's still, it doesn't even change blue if you do it right. You know, you can keep everything right in it. But that pattern we see on the screen there is on the front of pretty much every TIG set I've ever seen, right? And it allows you to just pin what you want. I'm getting some crater cracking. Let's increase the slope down time. I'm still getting some oxidization at the end of my weld. Let's increase the post gas and so on. Okay. So control. I know I keep saying that. TIG gives us control more than any of the other processes. Yeah. Right. So how do we start that arc? There's a couple of different main types. The first being scratch. Scratch is the most simple, okay? So what's required here is that we move the tungsten down and touch the tungsten from the electrode. We are then going to start passing electrical current through the tungsten and the workpiece. We then need to pull the electrode back up, and as we do that, because there was a short circuit, it will produce an arc as it jumps, and then we get our arc, right? The problem with that is that when we touch the electrode against the workpiece, it will stick during the short circuit, and pulling it back will probably leave a bit of tungsten in the weld, which is a tungsten inclusion. Tungsten inclusions are very hard areas of foreign material in the weld, so there's a higher chance of cracking from that point, okay, which we've got to be careful with. So it's a cheap way, it's not the best way of starting an arc. High frequency is probably the most common of all the modes of production. So what we have is we have electrode, but now we have a gap, and we press a button and we get a high frequency spark, travels through the set and starts our arc. So the tungsten never comes into contact with the workpiece. So we should have no no tungsten inclusion as a defect. However, you can set it wrong where you shock the tungsten and get the problem, which is that slope uppy deal we're gonna look at in the sentence. Okay, right. But the problem with high frequency is it can damage or interfere with electrical equipment. So when we're welding, if you've got a radio or something electrical nearby, it will interfere. It'll make it static. Okay, if you're in a hospital, it can turn off machines. If you've got a pacemaker, it can interfere with them, right? So we kind of like, we're in a rock and a hard place here. We've got scratch start that produces tungsten inclusions, and high frequency, which has a safety risk because of the electrical interference it can produce. It might not always be a safety risk, but we're going to worry about that. So how do we find something in the middle that's going to allow us to do something different? Well, this is lift arc, okay? Lift arc does a bit of both, okay? So what happens is we're going to bring the tungsten down, touch the workpiece, and a very, very small signal is going to be produced through that short circuit, okay? Not enough to make the electrode stick, just for the machine to detect, right, somebody wants to weld. As you then pull back up, the arc starts, because the electronics in the machine go, all right, okay, we're welding now. I detect the difference, away we go, and pushes it through. That's a fairly expensive bit of kit because of the controls which are in place to make that electrical control work, right? But it doesn't get tungsten inclusion, and it doesn't have a high frequency spark, so it's not going to interfere with electrical equipment, but it's a lot more expensive. By far, most sets use high frequency starts, and they last forever. So, there's still, we've got in our workshop, we've got welding sets there which are 20-year-old high frequency starts, still going, so they are fairly reliable. Okay, just got to be careful with it, and knowing it's dependent on where we're welding, especially TIG, where you're going to be welding on stuff like handrails in places like hospitals. There's this risk, and that's always captured within the risk assessments when you go to these places anyway, but we need to be aware of it. Okay, right, so the mode of electrical control is like MMA. It's a drooping characteristic constant amperage curve. So exactly in the same way as we had the MMA before, we're going to need to control the distance between the tip of the electrode, tungsten electrode, and the workpiece at all times. And if we don't control that gap, we're going to have a change in area to amperage, which is going to affect the width of the weld as well as the penetration. So we get exactly what we had with an MMA electrode, we just stick it into TIG now, okay? But the control we get from a constant amperage output is second to none, okay? But we're not trying to do a self-adjusting arc, so we don't need a flat characteristic, yeah? So that pushes through. So remember this, comes up a lot, questions where it says, which characteristic does a TIG set use? It's constant amperage. Which characteristic does a MMA set use? It's constant amperage. They're the same set, It's just how we fine control the output is different. Inverter sets, bulletproof, really good. Okay. Polarity. We talked about polarity this morning. And the effects, but when we deal with it over a tungsten, we do start to get some weird and wonderful things happening. So DC electrode negative is by far the main polarity we use for TIG. The only time we use AC is at aluminium welding because we need a cathodic cleaning. We'll talk about that when we do materials. But in DC negative, 70% of the heat is in the workpiece, 30% in the electrode. We need that because even though tungsten has a high melting point, it will still melt. So we don't want to overburden the electrode with it. We want to use the heat to melt the material, not the tungsten. right? That's always DC negative. So when in doubt, TIG is DC negative, right? If you need to take a guess, unless it's aluminium, then it's AC, right? We can see here on the picture, if we look at DC positive, so 70% of heat in the electrode, we get that heavy melting. So it's rounding off, it's becoming bulbous. There's no longer a point for the electricity to jump from the tungsten into the workpiece. So what happens is the arc starts to wander around this dome, right? So in AC and DC positive welding, you get much wider welds because the arc is wandering and has to go left and right, and generally makes it a lot wider, okay? So aluminium welds are always wider than steel welds, like for like, okay? But DC positive is not normally used. I say that because there's always somebody who turns out to be using DC positive, but in the main, TIG, as far as we're concerned as examination material, is DC electrode negative and AC. And that's it. We don't use it on DC positive. Okay, it'll generally just get you mixed up in the wrong answer if you try to think anything more complicated, even though in the real world it is more complicated. Okay. Right. So our preparations, you can see this what we'll do here. These first two are standard preparations for DC negative, and the next two on the right are preparations for AC. So what we have is for DC negative, we have to produce a point. Now this point from the tip to the bottom end of the prep, generally what we're looking for, that length is to be about 2.5 times the diameter of the electrode, right? And you see a lot of welders making them a lot longer than that. They're like javelin poles, okay? That's a negative. We don't want to do that. The longer and more skinny that electrode is sharpened to, the smaller the point at the end. The smaller the point at the end, the more likely it is that that's going to melt and burn off into the workpiece. We don't want that, okay? And as it melts, we lose the tip, our arc becomes more erratic, and we don't want that. I personally prefer a much more stubby end, like the one in from the end, which gives us a good point, good amount of control, least amount of melting. But for aluminium, we use an AC 50-50 heat balance. We know we're going to get some melting. So if I try to sharpen it like this one on the left, that's definitely going to melt and it's going to round off. So we want to get ahead of that and reduce the amount of melting, right? So you see this 1 second in from the right, we sharpen it like the left, but then we cut the tip off it. Just grind it back. And then some people just use it straight away like that and it melts back. But there are processes you can put it through, a little procedure to do a conditioning, which is low amperage, off on a different piece of scrap metal. You arc up and you allow it to melt off the job. So when you then take it to the job to do the proper weld, it's already rounded and you're going to have less chance of tungsten inclusions. Okay, so high-end stuff, you would do that conditioning. Some people don't. They just jump in at this stage, but there is a chance of tungsten inclusions. Okay, so we're getting tungsten inclusions in X-rays. This is what we need to look for: is how are we sharpening these tungstens, right? And I don't know if you can see on these pictures, can you see that the grinding marks are traveling up from the bottom to the tip in straight lines? That's because they've been done on a proper grinder. If you see people turning a 5-inch grinder on its back and sharpening tungstens like that, the grind marks are going to be around like a spiral, and that means that the flow of electricity is interfered with and you get more unstable welds. You'll also get off-kilter joint preps and things which increase the chance of tungsten inclusions. So a proper tungsten grinder with good, sharp, crisp lines is what you want. You don't want to cut the corners and use grinders. I was taught to use a grinder when I was an apprentice. That's all we were given, but it's wrong, and we need to do better. Okay, and it's dangerous. If you're sharpening a tungsten on the end of a grinder and the grinder catches the tungsten, where's it going to go? It's very light. I've seen somebody be sharpening a tungsten, the grinder catches it, and it flicked it away from them, but into somebody else's leg, right? And it's not. We need to be more sensible than that, okay? And encourage welders to reduce the length of the tungstens that they're sharpening. They don't need to be that long, okay? Right, so that's welding processes in the main of what we're going to talk about today. It's the first section to kind of make sure that we're all level and we start from the same basis. So when we do our next sessions in the future, we can kind of refer back to this presentation to pull in the different things. Like when we start talking about welding metallurgy, we're going to talk about MMA electrodes and how we can balance mechanical properties. We are going to talk about the welding of aluminium and how we use AC and cathodic cleaning. We'll talk about TIG welding back within that. The best advice I've got for you if you're preparing to do an exam or to do your official course is what you need to be able to do in your mind is produce a narrative. Right, I'm using this welding process. How does it work? What would be the implications of using that? Why would that happen? What could I do to stop this from happening? If you can build a narrative through a story, whatever question comes to you in an exam, you should be able to backfeed and jump in at any point of your story. Do not try just to commit multi-choice questions to memory. There are too many, right? It's just, there's thousands of potentials, right? And it won't help you when you go into a real job. You need to be able to say, right, what's my input? Therefore, what's the output? How do I change my control? And that's what we want to try and teach you here with this information, okay? So I'm gonna stop there. Thank you everybody for joining. It's been great to see the comments. With our next set of the next live stream, we'll start to move on into welding safety because we've done welding processes, so we'll do welding safety next, and starting to get into defects. So the types of defects, where you find them, how they look on both carbon steel and plastic samples. Okay, we're going to do that in detail. I know we get a lot of questions around things like how do defects look, where are they most likely to be. We've already had a question in the stream about slag and what defects can be on top of each other. How do we then make sure we're reporting in the right way to be able to pass the exams? I do a lot of one-to-ones where people come into our facility, especially if they've failed a part of their C-SWIP exam. So we will share our way of doing an exam, right? Because, again, I'm picking on C-SWIP here just because they're the main one people come from. But when you have an iPad, a set of samples, a report form, what are the best ways of capturing all that? We will do that in the next video, Okay, so we'll do defects and ways of reporting defects for these all in the next session. Okay, so if you're not already subscribed, please hit subscribe, right? It's like 70-80% of people who watch the videos aren't subscribed, so just, it's free. Click the button, come on. And please, if you're getting something from this, share it out with as many different people as possible. There's still a lot of people having to pay for knowledge that should just be free. Okay, and we want to make sure that's stopped there. Okay, great. So I will see you in the next one. We're going to try and do these fairly regularly. I'm actually going to try and look to do the defect one next week. I've just got to move some things around in my diary to make some time, because as you see, it takes quite a while out of the day. But next week we'll do defects and move on from there, and then weldability next after that for the really in-depth technical stuff. Okay, guys. So with that, then, thanks very much, and good luck with your studies, and have a safe weekend, and I'll see you later.